I hope you enjoy Simulation is Child's Play, Broken Toys Aren't. I'm Rob Stoppelman, the CEO of Optimal Device. At Optimal Device, we're an engineering consulting firm that's focused on design, analysis, and optimization. Here's my work from Case 18 about giving arthritis the finger. It took MRI data and used that scan data to create a customized medical device, in this case a finger prosthetic, and did FEA and fatigue analysis of that. But for today, we've got an emergency. The customer, Caitlin Stoppelman, who's 3.5, has a broken fidget spinner. She is not happy. It has multiple cracks, and 3 of the 4 bearings fall out easily now. The product is on the right, and we need to figure out what went wrong. I'm dubbing this talk Excessive Engineering because I'm basically taking a trivial product and applying every single technology that I can think of at it. So we go with CAD for CATIA for reverse engineering, injection molding with Simpo, FEA with Abacus, all on the 3D Experience platform. Then we go to topology optimization with Tosca, finish up with SolidWorks, and then 3D print it with FlashPrint. So let's get moving. We've got a lot of slides to go through. So first thing we gotta do is to break out my trusty calipers and do some measurements and also identify where the part failed. I had circled the 4 failures in red here, and one thing that's noteworthy is the way I have it oriented, there's a remarkable amount of symmetry to it. Right at the bottom center is where the injection molding was applied. So we take some rudimentary measurements, do some quick catting up, make sure there's good design intent. So at first, when I modify this dimension, the 6 that's highlighted in blue, the sketch kind of blew up. So just make sure that you're imagining how you're going to be designing it, what things you might change, and have it so there's design intent to your sketches. So after we had that sketch, we do a pad, or what SolidWorks would call an extrude. Then we do edge fillets, do a mirror, and a circular pattern. So quick and easy, all done with geometry. Now we take this geometry and we are going to do an injection molding simulation. That bottom cone is where the injection port was. I'm estimating it's a 3mm, and I'm also meshing with a 1mm mesh size. Aside from that, it's basically defaults using ABS plastic as the material, and we're just going to do a fill simulation. So we're not going to do a pack and fill, just a fill. So on the right, we've got the animation. The blue is where there's no material. The colors are showing the temperature of the material as it's flowing through, and it actually flows around and touches itself. Where those points occur, where one flow hits the other flow, is of primary interest here because the front of that plastic is a little bit cooler, and they're actually joined together, but it's a weak connection. So it's less strong there. It's a likely failure location. So you can see we've got on the bottom lobes, there's 2. On the top lobe, there's basically on the symmetry plane, there's 2 more. And when we look at the knit lines, on the right-hand side, we see we circled them. Actually, we circled on both. And the knit lines are highlighted with the little rainbow hue. And you can see they line up almost perfectly. So we have a root cause. We know why it's failing, where it is. I expect it's actually due to material shrinkage because this actually came out of a drawer after getting dusted off and actually had the crack. So I think the material is actually still shrinking with time, possibly due to humidity. So now, what can we do about it? Lots of times as an engineers, we're told, I need you to fix it, but don't change anything, which is lovely when you get that. So if I can't change the geometry, I can change where the injection ports are. So I've got 2 proposals. One on the left is the 3 cones that we're injecting at the outside edges of each lobe. An alternative that I could have gone with is the 3 blue arrows on the right-hand side. I chose the left one because I thought that it would provide a little bit more leeway in the manufacturing or in the design to make it so we can thicken it and stiffen it in these regions so we're less likely to fail because there's more material there. So then we do the same simulation as before, but now with 3 injection sites. And you can see now it flows around very symmetrically, so we didn't have that asymmetry as we did before, which should aid in the balance and actually make the product work better. But now we went from 4 failure sites to potentially 6 failure sites. So is that good or bad? I think it's okay because, like I said, we can modify the geometry there to make it so it's less likely to fail. And here's those 6 sites circled for the knit lines. So after this, I want to do some FEA analysis. So I weighed all the bearings because I didn't want to actually model bearings. So I'm just going to have representative cylinders that are using stainless steel material properties, but the density is modified to make it so the mass is appropriate. I find that the bearing could basically be determined as rigid compared to the ABS, but I find with sliding contacts and a lot of non-linearities, having a little bit of give to that otherwise rigid material actually helps a lot. So I tend not to use rigid parts very often. So here's the geometry. We've got it over in Abacus now. We've got it all meshed up. On the left-hand side is showing the contact, and it's actually an interference fit. So that means that one mesh is actually coinciding and actually penetrating the other to begin with. And during the first analysis step, you can actually remove these overclosures and generate the contact stresses that would happen if you did the press fit, but it's much more computationally efficient. The center bearing, the center of the center bearing I'm fixing for the second step, and then the edges, or the outside bearings, the centers of those, for the second step are being translated to basically extract out the center bearing. Because I don't know how much interference actually was in the design, because I got a failed part that's already splayed open and could have already been plastically deformed. So I went and looked at some other similar products and made a best guess on how much force it takes to extract out that bearing. I'm guessing it's about 30 pounds. So here's the stress analysis. The left-hand side is showing the stresses due to that overclosure. And then the right-hand side is showing with that bearing being extracted. And one thing to note is the bearing is stress-free now that it's been extracted. So literature varied a lot on what the frictional coefficient was. The highest that I found was 0.46. It seemed like there was a general consensus that 0.1 might be appropriate for ABS on stainless steel, but there was a wide range. So I did 3 different cases. I ended up getting to a sweet spot after 3 attempts. So 30 pounds it is. And that's a friction of 0.1 and a interference of 0.1 as well. So then I wanted to figure out what is like a real operating load. And I think it's if you spin this thing really fast that it basically wants to break apart and fly off. So a rotational load. So I found this video of some crazy people. Do not try this at home. They don't have safety glasses, and even if they did, they should not have done this, but it's hilarious and I love the sound. So as you can see, that thing just exploded. But I took the frames on either side. You can see on the left it's humming along, and on the right it looks like it's just the pads that you hold on to and the bearing. I think the entire plastic fidget spinner has actually exploded, flying off somewhere in their shop. So quite catastrophic. They estimated it was 50,000 RPM. I don't really know how they came up with that, but I'm just going to go with it. So if we're going to redesign this product, then we might as well make some changes and make it a little cooler. So the first thing I want to do is, it seems silly to me that you have bearings as the ballast because they have a hole in them and they're more expensive. So I looked at 2 other alternatives, nickels and pennies, doing a stack of each. Here's the diameters, thicknesses, how many you need to get to that thickness and what the mass would be, and then the cost of that. So pennies are the cheapest, bearings are the most expensive, but nickels are the heaviest. So I'm going to go with nickels because they still fit the same form factor, but they're going to bring a lot more rotational inertia. So they should actually work better than a traditional technique. So up until now, everything's been on the 3D Experience platform. All the different softwares, CATIA, Abacus, Simpo, and the great benefit of that is like when I was doing the modifications of the interference fit, I changed that on the CAD model. That propagates to the assembly, just like most CAD programs would do, but it also propagates to both the injection molding simulation and the FEA simulation and the meshes. So when I go into those simulations and try to view the results, it just says they're out of date. Would you like to resolve? It actually remeshes with the new geometry and resolves the analysis. If I did post-processing and I had, let's say, an auto-generated report, that generated report would actually auto-generate. So it's incredibly powerful with that. If I even changed a material property in the database, it would flag that that material property was used in this analysis, and therefore we need to resolve, etc. But I am going to step out of the 3D Experience platform for the next steps because there is topology optimization on the platform, but it's more of a designer level. It didn't have the capabilities that I needed, especially on the FEA side of it. So I'm actually going to jump out of the platform now. So I'm going to lose all that connectivity benefits, and now it's going to be more of a traditional workflow. So the design space that I've got is what's the maximum footprint that the fidget spinner could be. So because of ergonomics, there's only so much distance that you can pinch and be able to hold. So I'm locking in the design that they did the analysis to figure out what was ergonomic for their expected population of use. So children of whatever age. So I'm going to have it so it's a perfect circle on the outside, constant thickness, the thickness of a bearing, and then I'm going to let it optimize and chew away whatever geometry it wants, except you see these two concentric circles on either side of the bearings or the nickels. I basically want to have a continuous 2 millimeters of material around the bearing and the nickel so that they're retained well. After that, any other material, it's up to the optimization to decide what should be there. So we've got some symmetry planes on the left. I'm using a cylindrical coordinate system to make sure those symmetry planes are enforced. On the bottom right, we've got a fixed constraint in the Z direction, so to make it so it can't move in the axis of the bearing. So no translations in that direction. I'm applying a body force based off of that 50,000 RPM, just converted over from RPM to radians per second. And that's an extra one. So when I did the 50,000 RPM, when I got to 30% of the load, all that's in red was already yielding. So I believe that at least this design would not work for that speed, which this is a completely solid fidget spinner, so it should be as strong as you really could do with ABS at least. So I revised the simulation and just said it only got to 30% and it was that plastic, so I went to 10% of what they suggested, so 5,000 RPM. So now here's the optimization. So we've got energy stiffness, which is basically how efficient is the material being used to create stiffness for the part. We've got a displacement of the nickels, how far they're moving. So I'm trying to minimize that, and I'm trying to minimize weight. I varied the mass, the minimum mass allowed, and I did that for an engineering constraint like you'd normally have, like it needs to be less than this amount of weight, or if I have this much weight, I want it to be this stiff. I was actually varying that to make it look cool. So not very engineering-y, but this is for a presentation. I also made it so there was a symmetry plane through the thickness of the fidget spinner, so it was symmetric top to bottom. And then here's some of the bloopers that I got, and I thought these ones were particularly cool, but I did not understand what the optimization was trying to do here. It didn't seem like it was an efficient use of space, but they were kind of cool, so I'm putting them in my blooper reel. But I was doing a lot of this work last minute, so I am a member of Procrastination University, and 2 of the simulations that I stayed up probably to 2 a.m. to do were identical, and I didn't realize it till the next morning. So do your work early, like I tell my children. The reason why I was getting weird results is this energy stiffness measure. You actually want to maximize that, not minimize that. So you actually have to have a weighting of a negative value to make that work. Once I did that, I got the results on the left, which are starting to look a little bit more reasonable. You've got this web that's connecting all the bearings, and then you've got these struts that are starting to form, connecting the outside bearings. But for the final simulation, I actually turned off the energy stiffness as part of the objective function, because again, I was looking for a cool looking result, and I like the one that I ended up with without that. So without that, I got this. So we've got two struts connecting. We've got nice planar surfaces, which are going to come in handy for 3D printing. And then we've got some scalloping in on the top and bottom faces. And it has a traditional fidget spinner sort of look. In Tosca, you can post-process the results and view what percentage of the material is dense. So what Tots is actually doing is taking the elements, varying the density and the modulus of those elements, and trying to redistribute the mass throughout to be the most efficient. So over on the left-hand side is if the part had to be 99% dense, that element, it shows up, and that's what you get there. And on the right-hand side, it has to be 1% dense to show up. And then you basically get this solid shape that still is fidget spinner-like, but pretty boring. The 30% and the 50% look pretty good to me. 30% is actually the default setting if you don't change it in Tosca. But I actually liked 50% better, and conceptually I just like the idea. If it was half full, I use it. If it's under half full, I don't use it. So I went with the 50%. And then I brought this over into SolidWorks. You can save it out as an STL or as an IGES. And there are smoothing algorithms, and you can see any face that should have been planar or should have been cylindrical is. The other faces are more like an STL, but just in IGES format. I create a couple finger pad buttons. And now we're actually over to my 3D printer software. I use a FlashForge Creator Pro. And you bring it into the software, make sure that the flat surfaces are touching the print bed so they adhere well. That's why this design was particularly good. And then we slice it. It's going to take 40 layers. We're going to print over an hour and 50 minutes. And the weight is going to be 6.57 meters. Sorry, the distance, the amount of actual filament used. Just in case you're interested, here are the settings I use. Most importantly, I do 3 shells on the outer and top and bottom faces, and a fill density at 85% in ABS. And unlike what most people do, I actually like to run the fan after my first layer because I find it gets me better results, but that's abnormal. Here's the parts on my 3D printer, just when it gets done. And then if you wanted to do this, these are the type of bearings you want to search for. You can find ones that's specific for fidget spinners, or you can just take regular old bearings, take off the dust shield, and clean off the grease and oil it a little bit. You need to get the stacks of nickels and press fit it. I actually named my mallet Encouragement, but sometimes a heat gun or a toaster oven just to soften up the plastic or to heat up the nickels actually helps get it in there so you don't have to use glue. And here's the solution. The customer is very happy. And by the way, I forgot to say, she's Caitlin and 3.5 years old. And the product is shown on the right, and I think it turned out pretty cool. And my son's actually thinking about selling these online, so I'll be putting them on my blog post, how to get a 3D printed fidget spinner if you're interested in one. So feel free to contact me. On my blog, I'll put the fidget spinner files, a lot of the files that are in here, and the 3D printer files too. And if you have any questions about anything I've talked about, the 3D experience, any of the other softwares, about Optimal Device in general, or you just want to geek out and chat, that would be great. And I think it's time for questions, and thank you very much.